Let me share my screen. All right, I'm assuming you can see the screen. Hey everyone, my name is Frank Zhang. I'm an undergrad student at Cornell University. Today, Bill Liu and I will be giving an introduction to our recent work about the tight binding model for gallium oxide, wide bandgap semiconductor. To begin with, I'll introduce what is gallium oxide. It is what we call the wide bandgap semiconductor. And the reason why we want a wide bandgap in a semiconductor is that the wider the bandgap, the higher the breakdown field you can tolerate. And if you have a higher breakdown field, that means under the same voltage rating, you can make your transistor like smaller. And therefore, with a smaller channel, you can have a smaller resistance. And graph on the right shows you the relation between the breakdown voltage and the on resistance of a transistor given of different materials, and comparing beta gallium oxide to many of the conventional semiconductors. And you can be seeing that gallium oxide is giving a boost in the overall performance. And gallium oxide exists in 5 metastable phases. For the interest of power electronics, we're interested in 2 of them. The first one, beta gallium oxide, is the most stable phase. It has a monoclinic geometry, and the bandgap is around 4.9 eV. And the second one, alpha gallium oxide, is metastable and has a corundum structure and the bandgap around 5.5 EVs. And their crystal structures are shown on the right here. And just for comparison, some of the traditional or previous generation wide bandgap semiconductors, like gallium nitride, has a bandgap around 3.4 eV, and the silicon carbide has a bandgap from 2.3 to 3.3 eV, depending on which polymorphism you're looking at. So now we know what is gallium oxide. Let me introduce to you what is tight binding model. And I'm showing you a toy example here. It consists of a 5-atom conducting channel. And for simplicity, I'm assuming for each atom, there's only one atomic orbital. Each atomic orbital has its own energy, which we call on-site energy. And there will be an interaction across different atoms. And for simplification, to make a simplification, we're assuming that the interaction only happens at the nearest neighbor, meaning the atom 1 interacts with atom 2, atom 2 interacts only with atom 3, and so on. And we call this energy negative T, or hopping energy. Overall, the system can be described by the matrix, a 555 matrix shown below. The diagonal elements are the on-site energy, and the off-diagonal elements are the hopping energies. And because we're only including the nearest neighbor hopping, we only have one sub-diagonal that is non-zero on each side. So we have the matrix now. We just have to find the eigendecomposition of this matrix, and we know pretty much everything about systems, such as the electron transport behavior. Okay, now we know what's the tight binding model, but why do we need a tight binding model? The reason is that device engineers want to simulate the behavior of their device, and tight binding model can do exactly what they want. Like the one shown on the left, we can consider this 5-atom channel as a channel of a transistor, and we can do some simulation. The benefit of tight binding model is that it contains the full information about the electronic band structure. You can define the device structures atomically, like I can place the atoms anywhere I want. And it's also computationally efficient to solve. You just have to solve a matrix, which is much cheaper than some other first principle methods such as density functional theory. And just to give you some specific numbers for gallium oxide, we have 4 gallium and 6 oxygen atoms in one primitive cell. We only consider the s and p orbitals of gallium and the p orbitals of oxygen because they are the energetically most related to mobile electrons in the conduction band. And in total, we have 34 orbitals per unit cell.
So we used 2 basis sets for our tight binding models. The first method uses atomic orbital basis to find a semi-empirical fit to the DFT band structure. And the second method transforms DFT to real space and constructs the model from maximally localized Werner function. Here are DFT calculated band structures for beta and alpha gallium oxide. It is well known that DFT calculation underestimates the band gap by a factor of 2 or more. In type binding model, this problem can be fixed by tuning parameters to match the experimental band gap values. So in the first method, we assumed the following relation of the hopping energy. We used one energy scale multiplier E naught, which is dependent on the types of atoms and atomic orbitals. Then we assigned a power decay trend in atomic distance R of this energy prefactor using a constant typical bond length in the crystal A naught and a decay factor N. By tuning E naught and N in this relationship, we were able to characterize the hopping energies between different atomic orbitals interactions. And in the second method, we used a different local basis from atomic orbitals. The parameters of the maximally localized Wannier function can be directly generated in DFT calculated matrix. It is a routine method built in DFT code. Yeah, so can you go to the next slide? Here are 4 band structures plots that our type binding model produced as compared to DFT calculated band structures. The solid blue curve indicates the type binding model, and dotted green curve represents the DFT model. The A and B plots are from semi-empirical calculation based on atomic orbitals, and C and D plots are from direct calculation based on the Wannierized orbitals. As you can see, in the first method, our type binding models accurately reproduce many features, including conduction band effective mass, flat valence band edge, and high conduction band level at gamma point and the secondary value at the T point. For the second method, the model fits even better because it is directly derived from DFT model. Can you go to the next slide? And finally, by tuning parameters in the calculation based on the atomic orbitals, we were able to correct the band gap in type binding models while maintaining the band structure features that we care about. So here, these 2 graphs shows our final results. Oh, can you go to the next slide? So to sum up, we developed a type binding model for beta and alpha gallium oxide from atomic-based and Wannierized orbitals. The band gap corrected model will be used for device simulations in the future. And that's all we have. We want to thank everyone who has helped us a lot, especially Professor Jenna, Professor Shane, Guru, and Nick, and many others who helped us a lot. Now we welcome any questions.
We can't really, because it's a video. But all right, let's just, and